So we're talking about acids and bases, and last time we sort of finished up talking about salts. We talked about the three really different types of salts that we come across. First off, salts are obviously obtained from really a reaction of an acid and a base together. You create, as you know, water and a salt. Salt's an ionic compound. The salt part has the ability in certain cases to really continue to react. And what it's going to really react with is pretty much water. And it's going to go through a reaction that's known as a hydrolysis reaction. And in certain cases, the salt will continue to react. In other cases, it will not. What really determines whether or not that salt will continue to react is really where it came from. So the other day we sort of were thinking backwards about, sort of where some of these salts originated from. And if the salt basically originates from anything that's really strong, its partner, which is basically the salt, will be relatively weak. And what that means is those things are considered basically neutral salts, where the pH should be 7. So more specifically, anything that really comes from group 1 or 2 on the periodic table, which is really where a lot of our strong bases come from. So those things like sodium, potassium, those things are considered neutral salts because they, in essence, do come from a strong base. Now, if the salt kind of originates from a weak acid, then its conjugate base, which would be part of the salt, would go through hydrolysis. And it would go through hydrolysis, basically reacting as a base, which means it will essentially accept an H plus from water, which is what we see here on the bottom. So basically what's going to happen is the acetate here, which comes from acetic acid, will basically pick up the H plus from the water. The result of that is we're going to generate hydroxide in this solution. We're going to generate more free hydroxide in the solution. The result of that is we would expect that solution to be basic because of that. So it will go through hydrolysis. It will actually produce hydroxide. As we also talked about when we do calculations that involve these guys, we will be usually given the wrong K value, as we sort of talked about. So we could use that Ka times Kb equals Kw to sort of get to what we need. The thing you want to keep in mind, as we talked about last time, is if you see your equation and you have hydroxide on the product side, you should be using a Kb when you are calculating something like pH. Obviously, when you would do it, you would do an ice table. You would use the appropriate Kb value. When you solve for X, that would be the hydroxide concentration. That would allow you to calculate the pOH and then get yourself basically to the pH. The other type of salt is a salt that really comes from a weak base, like this guy here that I think we looked at. And a salt that comes from a weak base will be a relatively strong conjugate acid, and it's going to basically act as an acid. So it's not really written here, but I think I did it on a separate slide the other day. This is basically what is happening in this reaction. In this case, it's actually going to be the conjugate acid here donating its H plus, which is the definition of what an acid will do. The result of that is we will produce H3O plus on the other side. The production of H3O plus automatically tells us, without really even doing a calculation, that we would expect that solution to be acidic. If we did calculate the pH, you would do again an ice table here where you would solve for X. Here you would again want to be using the correct K value. Probably are given the wrong one in this problem as well. And when you solve for X, that would be the H3O plus concentration, which means you could go directly into the pH equation and you would be done at that point. Any question on that stuff we talked about last time? There is another way that you could kind of generate an acidic salt, and that is really small, highly positively charged metals, like transition metals sometimes. They actually can behave kind of like an acid or create an acid solution. So if we look at something like this, which is our aluminum with basically 6 waters attached. So we essentially got aluminum, and attached to it, we have basically 6 waters coordinated around it. 1, 2, 3, 4, 5. And I'll draw the one out here like so. And this guy would have an overall charge of +3 because the aluminum has a +3 charge. Water is neutral, so it has no charge. What's going to happen in this situation is another water will come by, just a regular old water. And basically what will happen is one of these H's will then head on over to the water. The result of that is it will make H3O plus, which is the hydronium ion, which is here, and would create an acidic solution. In case you're curious about this scary guy here, you will know how to name it before we're done with this semester. But just to keep track of what everything happened, we pretty much have 1, 2, 3, 4, and 5 waters that are still intact, which is what we see here. One of the waters lost the H, which leaves it as an OH, which is where that comes from. And obviously the aluminum in the middle. OH is OH minus, right? And aluminum is +3. So -1 and +3 gives us a +2 that's left over. So that's the pieces that are basically left over. In relation to what we're talking about is basically this formation here of our H3O plus, which would make it acidic. So a lot of transition metals with your +2s, +3s, you know, kind of have the ability to sort of do that. And they are also sometimes referred to sort of as acidic salts, a little bit different than a sort of a normal salt in that case. By the way, that is what aluminum is in solution, basically, right? When it says aqueous next to it, that's basically what the aqueous means. It's surrounded by a bunch of waters. So that is basically what, you know, is going on there on the left-hand side. Any questions on any of that there? All right, then why don't we try some here with some calculations perhaps and see what we got. Why don't we start with this one? What is the pH of a 0.5 molar KCl solution? Okay, let's take a look at this one really quick here. So this is KCl, which is our salt solution, which means really when it's in solution, it's going to 100% break apart into a K plus and a Cl minus. So really when you look at the salt, you really want to kind of look at both of these and try to determine, you know, what's going to happen, if anything is going to happen in this case. So if we had to take a guess as to sort of where the salt came from, what would the acid most likely be? Hydrochloric acid, right? The base probably would be potassium hydroxide, perhaps. Yeah. And that would give you like KCl and some water, right? So that means really K, which is group 1, in reality probably came from this base. KOH and group 1 are relatively strong, right? Which means will K plus do anything and continue to react? It will not. It's neutral, right? So pH there of 7, basically. How about the Cl minus? Cl minus came from HCl, which also is a strong acid, which means the Cl minus would also be a neutral salt, right? Which means there is really no calculation in this case because it basically comes from strong acid and a strong base. We would expect the solution to be neutral because basically both components of the salt will not react with water or produce any more H plus or any more OH minus. Any questions on that there? All right, so let's try one where there is a calculation. This one you do need to calculate. So see what you come up with here. You should calculate by doing an ice table. There should be some hydrolysis happening. Write the correct equation. Figure out what the pH would be. We actually want to know what is the pH. I guess I never really asked what the question is. Let's do that. All right, let's take a look and see how we're doing. So obviously we have sodium fluoride here, which is a salt. That basically means when sodium fluoride's in solution, it will break apart into a sodium ion and a fluoride ion. So the goal here is to decide, is anybody basically going to continue to react with, say, water and affect the pH? So sodium, we should know, because it is group 1, will it do anything to affect the pH? It will not. It is a neutral salt. It comes most likely from sodium hydroxide, which means really it's not going to do anything to affect the pH. So that means we will turn our attention here to F minus when we have to decide, will this guy basically do anything to change the pH? F minus most likely came from, yeah, and you don't want to overlook like the key that is here in the problem, right? The HF is really a Ka value, right? And that means that's a weak acid. So that should automatically tell you that's going to be relatively strong. And it's also where it came from. So very often these type of problems, they'll kind of give you where it came from. And clearly, if you see a K value associated with it, you know it's weak, which means you know that that part of the salt will go through hydrolysis. So we are going to get the F minus that's going to go through hydrolysis. And that's just a fancy way of saying it is going to react with water, basically. So the key is, will it give an H or accept an H? Logic would tell us it cannot give an H, right? But just in case we don't have that logic with us or we can't figure that out, we do know that it came from HF, right, which is a weak acid. That would mean that technically speaking, this would be like the conjugate base. And the definition of a base is something that will accept an H plus. So when it reacts with water, it's going to react as a base and it's going to accept the H plus. And that is what we would expect to see here. The H plus go from the water over to the F minus. That is then going to give us what always happens, which is it will make exactly where it came from. So if you're ever like in trouble of I don't know what it's going to make on the other side, don't overlook again what is in the problem here, because that will help you. And that also will produce OH minus. Any questions on the equation there? Without doing a calculation, this solution should be acidic, basic, or neutral. Should be basic because we are producing OH minus. When we do the calculation, we also should be using a KB. Again, here, very common, not given the correct value. So at some point, we will need to change that to the KB value in order to get the correct answer. The rest of it here is going to be like a regular ice table. We're going to initially start with the concentration in F minus, since this is a 1-to-1-to-1 relationship, because the whole thing is 0.3 molar. The concentration of F minus would be 0.3 molar as well. This would be 0 and 0. Change would be minus X, plus X, and plus X. That would get us 0.3 minus X, X, and X. This again would go into our KB value, as you correctly said there, and that would be our HF, our OH minus, divided by our F minus, obviously leaving water out like normal. That's going to give us X squared divided by 0.3 minus X. We do need to do that conversion to convert it into the KB. So remember that the KW equals KA times KB, which means that the KB in this case would be 1 times 10 to the minus 14 divided by our Ka value, 7.2 to the minus 4. And that is going to give us looks like we'll call it a 1.4 times 10 to the minus 11. Any questions so far? All right, what's left is basically to take this guy here and we want to solve it. So I'm going to flip page here and do that. So it's 0.3, maybe. Go. All right, so we had X squared, 0.3 minus X equals 1.4 times 10 to the minus 11. That looks like a very small value, so I'm going to assume that x is equal to 0 in this case. That's going to give me an x squared over 0.3 is equal to 1.4 times 10 to the minus 11. Going to multiply the 0.3 to the other side, also do a little square root action on it. And that will give me an x value of 2.04 times 10 to the minus 6. We do want to check it. So again, a reminder to check, we would divide it in this case by 0.3, times it by 100%, and I think we should be good, I believe. We are nowhere even near 0.1%, so we are good on the check here. Yes, sir. How did I get the 1.4? I did the KB equals KW divided by the KA. So 1 times 10 to the minus 14 divided by the 7.2 to the minus 4, I believe. Yeah. I got that right. Yeah. Other questions? All right. At that point, that is a good. That means that looking at our ice table, a reminder that this actually equals the hydroxide concentration, not the H plus concentration. That means that we can get the POH. I take it minus the log of 2.04 times 10 to the minus 6. That's going to get us minus the log 2.04 to the minus 6. We'll call it a 5.69. That again is not the pH, but just the POH. Finally subtracting our 14 there. Going to yield us a, looks like maybe 8.31, if I did that right. That is a basic pH, and that is what we would expect, right? Based just on the properly written equation. Any questions on any part of that there? All right, one short. The next one you got there, I think. Yeah, I'll put it up on bar. Let's give him. There you go. So what's the pH of this sodium cyanide solution? That's 0.75. So again, here we have a different salt, which is sodium cyanide in solution. We are going to get it to basically break apart. So like in the previous one here, we already know sodium is group 1, which is really neutral, so we don't have to worry about it. Again, anything in group 1 or group 2 pretty much are going to be neutral. Here we do have the cyanide here, and again, in case you were not sure where it came from, they were nice enough to give us a little bit of extra information here. We can see that that came from HCN, which is a weak acid, which means we would expect this guy to go through hydrolysis. Since it really came from HCN, when it reacts, it's going to react as a base in this case, and that would get us our CN minus plus our water. And again, since it is reacting as a base, we would expect it to accept the H plus. Again, logic tells us it cannot give an H plus because it doesn't have one. It will again make where it came from, which is HCN. And again, here we will produce hydroxide in this case. And without picking up the calculator, we should already know that this is going to be, again, a basic solution. Any questions on the equation there? We're going to roll through the ice table very similar. So we're going to go 0.75, which really comes from the sodium cyanide concentration. That's going to be 0 and 0. We're going to have a minus X, a plus X, and a plus X. That means at equilibrium here, 0.75 minus X, X, and X. This should go into our K, which is our products divided by our reactants. And by the way, this is a K Yeah, so it should be a KB. Again, we see the hydroxide. We need to make sure that we do use, again, the KB. We're going to do our little flip there by taking 1 to the minus 14 and divide it by 6.2 to the minus 10 in this case. And if we do that, we end up with using our KB is KW divided by KA. Looks like 1.6 times 10 to the minus 5 will be our KB value here. That means that we had x squared divided by 0.75 minus x, I believe, right, is 1.6 times 10 to the minus 5. Again, here, might as well give it a shot and assume that x is equal to 0 in this case. And that would get us x squared divided by 0.75 equals 1.6 times 10 to the minus 5. Any questions so far? Yeah. How did I get the 1.6 times 10 to the minus 5? Yeah, so I took the Ka value that they gave us, which was 6.2 to the minus 10, and basically took 1 times 10 to the minus 14, which is Kw, divided by 6.2 times 10 to the minus 10, and that should convert it into our Kb value. Yeah. Other questions on that? You're welcome. So same math here. We're going to multiply the 0.75 to the other side and also take the square root of it. So 0.75 times, not that number, try that again, 1.6 to the minus 5. Do a little square rooting. Looks like we end up with an x of 3.46 times 10 to the minus 3. We'll do a little check here to make sure we're okay. So we'll divide that by 0.75, times it by 100, and it looks like we're at like 0.4%. So the check here is good in this case. Again, going back to our ice table, we see that the x does equal the OH minus concentration in this case. So once again, we will calculate our POH off of it. And it's like a 2.46 here. And our pH then would be 14 minus 2.46. And that is going to get us an 1154, which is definitely a basic pH in this case. Any questions on any of that part there? Any questions on salt? So we did a couple of basic salts here. Acidic salts basically work the same way. You're going to do an ice table. You'll have to switch out the value to a Ka value in that case, because you will produce H3O plus. The only difference is you could go directly into the pH equation, obviously, with an acidic salt, because when you solve for X, it will be the H plus concentration. Questions? Yeah. I will say specifically in salt type problems, it's very common that they give you the wrong K value. So I would say yes, specifically for salts, but you may get somebody that's nice and give you the right one, but most of the time they'll give you the wrong one. Yeah. Yeah. That's basically it's a simple rule. Basically, if it comes from really group 1 or group 2 on the periodic table, except for beryllium, it's going to be a neutral salt. You don't have to worry about it. And it's really for the reason we've been talking about, even though they say group 1, group 2 on the periodic table, it's really because it does really come from a strong base in most cases. Is really where it's generated from. And like sodium hydroxide, because remember, group 1 and group 2 on the periodic table is pretty much where all of our strong bases come from. And so if you have basically a part of a salt that comes from there, it's going to be relatively weak and essentially neutral. Yeah, you would probably be given KW. It's a good number to know. We use it a lot. So, you should probably know it, but it'll probably be provided to you. Other questions? All right, so these are salts. Obviously, you need to be able to write the equations, right, that's going on here with these salts. You need to be able to solve for the pH. Any questions on any of that? Okay. Here's a prettier picture of the aluminum than I drew, but same idea. Again, that's our aluminum. Going to pull off one of those hydrogens and produce H3O plus. Now, in all these examples so far, only really one part of the salt went through hydrolysis. So for example, in the last one, just the CN minus went through it. The sodium part did not. It is possible that you could hit a salt where both parts of it will go through hydrolysis. You know, if you had something, say, like NH4NO2, yeah, that came from probably NH3. That came from nitrous acid, not nitric acid, but nitrous acid. Both are weak, which means technically speaking, both parts of this salt could go through hydrolysis. So if you wanted to calculate what the pH would be when you have both parts that go through hydrolysis, it's quite complicated. So what we end up doing is we actually compare the Ka value to the Kb value, and whichever one is larger is sort of the problem that you would do. So for example, if you compare the Kb for the anion, the negative guy, to the Ka for the cation, and the Kb is larger, you would assume that this solution would be basic, and you would really do the Kb problem part of it and sort of ignore the other part. If the Kb for the anion is less than the Ka for the cation, or the Ka value is larger, you would assume that this solution would be acidic, and you would basically do the Ka problem if you were trying to calculate the pH. And if you happen to have a Ka and a Kb that are essentially the same number, that is going to get you a neutral solution, or a pH of 7 in that case. So there are certain cases where you will have basically both parts of the salts that will go through hydrolysis. We would like to compare the Ka to the Kb, and whichever one's larger, that's basically the one that you do. And it will either be obviously an acid if it's the Ka, or it will be a base if it's the Kb that's larger. Any questions on that there? Okay. The key to some of that is you do want to make sure that you actually grab the correct values to compare. So just be careful when you do that. Here are oxides. So these are oxides, and there are some that are basic oxides. So basically, when these guys over here react with water, oxide means obviously something with oxygen. They produce really our strong bases, like when this guy in water, sodium hydroxide, potassium hydroxide, and so forth. Pretty much our nonmetals over here are kind of bluish guys. These guys, when they react with water, basically will produce acids. So for example, if you take some water and a little CO2, right, you get some H2CO3, which is carbonic acid. So you could generate some carbonic acid. A couple of like N2O5s will actually generate some nitric acid. So those guys on the upper right are what are referred to as acidic oxides. Guys on the left there are basic oxides. And there are some that are amphoteric. Amphoteric means that, again, it could act as an acid or a base. So they could kind of go either way in those situations. Now, we've talked about the Arrhenius definition of an acid and base, the Bronsted-Lowry definition of acid and base. There is another definition of an acid and base, which is really important, and that's our good friend Lewis acid and Lewis base. When we think of Lewis, we think of Lewis structures, yes, and with Lewis structures, we think of electrons. So Lewis's definition involves electrons. A Lewis acid is a substance that will accept a pair of electrons, while a Lewis base will be one that will donate a pair of electrons. So the Lewis acid and base definition is it's a good one. It's one that we come across when we talk about transition metals and coordination compounds, but we're talking about a pair of electrons. Typically speaking, in order to donate a pair of electrons, things that are good Lewis bases, These are things that are negatively charged a lot of times, because when you're negatively charged, that means you have gained electrons. You got some to donate. Also, things that are polar, that have non-bonding electrons, like water, right? When you draw water, you got some of those non-bonding electrons on the oxygen. It's a polar molecule. Polar molecule means there's separation of charge, makes it a really good Lewis base. So here's an example here. It's actually going to be our hydroxide here acting as a Lewis base, donating to our H+, which is technically electron deficient. That's why it has a positive charge, right? Things with positive charges are basically lost electrons or electron deficient. And this would be our acid, and that would be our base in this case. Same thing here, that's ammonia. It's a polar molecule. It's got the non-bonding electrons there, going to donate over, making ammonia our Lewis base, and our H+ here, our acid. As you can also see, if you use the Bronsted-Lowry definition, you get the same result. H+ being donated means that's the acid, and the other guy accepted H+, which is the base. Same thing here. So this is another definition of an acid and base involving electrons being transferred. The nice thing about it is you can apply acid and base sort of theory to things that really don't involve H+. So for example, if we look at this guy here, that is boron, which, as you probably remember, is an exception to the octet rule. It is an incomplete octet. It's got less than 8, and it's happy about that. But because it does have less than 8, it is electron deficient, which means that these electrons here will come over, and we will make that bond here, making again this our base, our Lewis base, this being our acid. And in this case, there's actually no transfer of a proton in that particular case, and we could still sort of apply sort of the acid base chemistry to it. Any questions on Lewis acid and base? So a little bit opposite of Bronsted, and also dealing with electrons, while Bronsted-Lowry deals with H+ that are being transferred. We will see more of Lewis bases for sure when we talk about coordination complexes and complex ions and transition metals a little bit later on in a different chapter as well. All right, so the last thing we're going to talk about in this chapter here are polyprotic acids. So polyprotic acids are acids that basically have more than one H+ that they could give away. The H+s do come off basically one at a time. And for each H+ that comes off, you do get a Ka value, for example. So if you look at, say, phosphoric acid, the first thing that would happen is the phosphoric acid here will drop an H+ and make H2PO4 minus, and there would be a Ka1 associated with that. The next thing that happens is that H2PO4 minus will dump the next H+, and that will make HPO4 2 minus, and that would be our Ka2. And lastly, our HPO4 2 minus will dump the last H+ off and make our phosphate, which will be Ka3 in this case. We sometimes think of them all popping off at once, because if you take all these guys together, this cancels, and we end up with what you normally think of probably when you think of something like this, H3PO4, which is the overall reaction going to 3 H+ and phosphate. So sometimes it's misleading when we look at this equation, because we think they just all pop off at once, but it actually is a stepwise fashion that's occurring. Is it easier to remove the first H or the second H? Which one is easier to remove? The first H is much easier to remove. When you do that, you go from something that's neutral now to something that is negatively charged, which you then want to extract and thing that's positive, so that you're going to hold it a little tighter, makes it harder, even harder to remove the third one. And we see that when we look at these Ka values. This is the Ka value for the first one. which is 7.5 times 10 to the minus, I think it's this 3. Then goes to 6.9 times 10 to the minus 8 to 4.8 times 10 to the minus 13. The Ka value gets smaller. Because the Ka value gets smaller, that means we have mainly reactants or products. Small K value means mostly reactants, which in this situation would mean we're basically hanging out over here. Not very much of this guy is coming off at that point. So as that Ka value gets smaller and smaller, less of the acid will come apart, which means much harder to get rid of that third hydrogen at that particular point. We see that trend all the way across here on this table. We even see sulfuric acid up here, which gives you a value of large, which is not very helpful, but it's on this table because it is the second guy that's actually a weak acid. So when something like sulfuric acid breaks apart, H plus and HSO4 minus, it's actually this guy here that's a sort of a weak acid that will break apart into sulfate. Yeah. So that number is not very helpful there, the large, which is why we consider sulfuric acid large. But if you're dealing with it after it's lost the hydrogen, it kind of becomes more like a weak acid. So when we do these type of problems, we can furnish basically one proton at a time. It always dissociates in a stepwise manner. And for a typical thing, we really do see the Ka1 is much larger than the 2 than it is the 3. By the way, just so we're clear, this is a generic, right, for a monoprotic acid. Monoprotic means it has just one H plus that comes off. The H plus is always the cation. The A actually has a -1 charge, right? Diprotic is H2A. Again, comes off one at a time, but here we actually have 2 H pluses, which means the charge on that is -2, like sulfuric acid, SO42 minus. And obviously, if you needed a generic for a triprotic acid, it would be this guy here, like phosphoric acid, 3 H pluses, where the charge on the negative guy is -3, like phosphate is PO4 3 minus in this case. So let's talk about how we go about doing these problems. So what is do this problem? What is basically just find everything out about phosphoric acid. So we're going to take a solution of 5 molar phosphoric acid. We eventually want to figure out what is the pH of it, what is the concentration of phosphoric acid at equilibrium, what is the concentration of H2PO4 minus, HPO4 2 minus, and phosphate H plus, all at equilibrium. So this is a triprotic acid. These are the Ka values that we got going on there. So the very first thing that's going to happen is basically the phosphoric acid is going to ditch basically one H plus. So we will have our H3PO4. It will give away an H plus. It will leave us a H2PO4 minus. And this is our Ka1, which, as we saw on the previous slide there, is 7.5 to the -3. All right, so we're going to basically do an ice table here. It is a weak acid, obviously. We have a Ka value. Initially, we started with 5 molar phosphoric acid. We got 0 and 0. Change is going to be -x plus x plus x, giving us 5 minus x, x, and x. This is going to go into our Ka1 expression, which is our H plus times our H2PO4 minus, divided by our H3PO4. That obviously equals to 7.5 times 10 to the -3. Putting my numbers in, I get x squared divided by 5 minus x is equal to 7.5 times 10 to the -3. I'm going to assume that x is equal to 0 in this case, giving me x squared divided by 5 is equal to 7.5 times 10 to the minus 3. Multiplying the 5, taking the square root. So 5 times 7.5 to the minus 3, and doing a little square root action there. That is, bless you, that's going to give you an x that is 1.94 times 10 to the minus 1. We want to check it, so we're going to divide it by 5 and times it by 100 and hope for the best here. Divide it by 5 times 100, and that would be why I changed the number from the original number. That is 3.87%, which means we are good. Thank goodness. All right, so we now have an x value at this point, and if we look at our table, this will give us, from the very first table, a bunch of information. It will give us the concentration of H3PO4 at equilibrium, and that would be 5 minus 1.94 times 10 to the minus 1, and that would get us about 4 we'll call it 81 molar. It will also give us the H plus concentration, which is equal to X, which means it is 1.94 times 10 to the minus 1 molar. It will also give us from our table the concentration of H2PO4 minus, which also equals X, which would be 1.94 times 10 to the minus 1 molar. So from this very first table, we were able to knock off a couple of things off of our list. We were able to knock off that guy, and I believe this guy and this guy. So we still got a few more things we're looking to find, but at least from this first table here, we're able to sort of calculate several things. Any questions so far? We're going to talk about that in just a second. We're going to leave the pH to the end, and it'll hopefully answer your question as well. Yeah. Okay, so because we really want to find about everybody there through all the different steps, we got to continue on basically to the second step, which is the second hydrogen coming off at this point. So the next step would be the H2PO4 minus will drop another H plus, giving us HPO4 2 minus. Looking back at our original, that is the Ka2, which is 6.2 to the minus 8. So that is 6.2 times 10 to the minus 8 Ka2 in this case. So this is sort of a continual dissociation that's happening. Where do I get my initial concentrations of this guy? My initial concentrations of this guy would come from the previous table equilibrium concentration. So that would be 1.94 to the minus 1 in this case. So we would have 1.94 times 10 to the minus 1, again coming from the equilibrium step. Do I have some H plus in the solution at this point? I do. It also comes from the previous table, which happened to be the same number, I believe. 1.94 times 10 to the minus 1. And here we have 0 for the last guy. So we're going to use our equilibrium line from the previous table to carry over to our initial line here. The change is going to be minus X plus X plus X, which means at equilibrium, 1.94 times 10 to the minus 1 minus X. 1.94 times 10 to the minus 1 plus X. Remember, that is plus. Most people are like minusing at this point. And that would be X. This would go into our Ka2 expression, which would be our H plus, our HPO4 2 minus, divided by our H2PO4 minus. And that would be basically, in this case, 1.94 times 10 to the minus 1 plus X on top times X. divided by 1.94 times 10 to the minus 1 minus x on the bottom, and that would equal our 6.2 times 10 to the minus 8. Any questions so far? Had luck on the first round there with my assumption, so I'm going to do the same thing here. I'm going to assume that x is equal to 0. In this case, that is going to get rid of, again, this x and this x. That would get me 1.94 times 10 to the minus 1 times x divided by 1.94 times 10 to the minus 1 equals 6.2 times 10 to the minus 8. I think I could do this math. That is going to cancel. That means that my x value here would equal 6.2 times 10 to the minus 8. Any questions on that there? We again want to check it, but you are probably going to be good since the first one was good. So 6.2 to the minus 8 divided by 1.94 to the minus 1 times it by 100, and you're like 0.0000 something percent. The check here is good. And again, we would be dividing by the 1.94. So now filling this into our table, this gives us the concentration at this point of HPO4 2 minus, which would be 6.2 times 10 to the minus 8 molar in this case. What is our concentration of H plus at this point? What do you get when you take 1.94 times 10 to the minus 1 and you add 6.2 times 10 to the minus 8? You end up with 1.94 times 10 to the minus 1 still. Same thing with the H2PO4 minus. If you take 1.94 times 10 to the minus 1 and you subtract that number, you will still end up with the same number. So these guys' concentrations did not really change all that much, and they're actually still the same at this point. So if you put it in, you'll still get the same number. Any questions on that point? So after our second table, we can go back to our list here. We just got this guy's concentration. That means the one last thing that we're looking for is our phosphates concentration. That is going to require us to get down to the third reaction here, because that's really where phosphate shows up. So let us do that third one here. So the third thing that's going to happen is our HPO4 2 minus is going to give up the very last proton there. And we're going to make phosphate, which is what we're interested in, which is why we have to go this far, obviously. And we're going to use that third Ka value, which is 4.8 to the minus 13. So that is 4.8 times 10 to the minus 13 Ka3. So our initial on this table, just like we did previously, will come from the last table. So our HPO4 2 minus from the last table is 6.2 to the minus 8. So that is what we get here, 6.2 times 10 to the minus 8. Do I still have H plus there? I do, and as we saw from the last table, it really didn't change concentration. It is still 1.94 times 10 to the minus 1, and this guy is 0 at this point. The change here going to be minus x plus x plus x, giving us 6.2 times 10 to the minus 8 minus x, 1.94 times 10 to the minus 1 plus x, and x. Going into our Ka3 expression here, H plus PO4 3 minus divided by HPO4 2 minus. And that would get us up on top 1.94 times 10 to the minus 1 plus x times x divided by 6.2 times 10 to the minus 8 minus x is equal to 4.8 times 10 to the minus 13. No need to stop now. Let us assume that x is equal to 0. I have a good feeling about it. That again is going to get rid of our x's up here and down here. That is going to get us 1.94 times 10 to the minus 1 times x up on top, divided by 6.2 times 10 to the minus 8 on the bottom, equals 4.8 times 10 to the minus 13. We're going to multiply the bottom to the other side and divide by what's on top there. So that's 4.8 to the minus 13 times 6.2 to the minus 8. We're then going to come back and divide by 1.94 to the minus 1, giving us an x value of 1.53 times 10 to the minus 19, which again, we do want to check just to be safe. So we'll do either one here. Should be all right, I think. So we are good, I think, on either one. So again, the check is good here. At this point, that would give us the concentration of PO43 minus, which is equal to X, 1.53 times 10 to the minus 19 molar. Again, in terms of the H plus concentration, when we put that value back into here, does this number change? It does not. It's super small, this number we just got. Same thing here. When we put it back into here, it technically doesn't really change either. And that gives us our phosphate answer. Any questions first off on the different tables here and how we got to where we got to? All right, so by going all the way to the end here to come to your question, what did we actually see as we went from the first hydrogen to the second hydrogen to the third hydrogen coming off? The very first hydrogen that came off came out at a concentration of 1.94 times 10 to the minus 1, basically 0.194, basically, right? When we came and got the second hydrogen off, we basically achieved only 6.2 times 10 to the minus 8. Not very much came off in that second step, right? As we talked about earlier, it's much harder to take off the second one than the first one. We see that with the Ka value. And when we got to the third step, even less came off, right? 1.5 times 10 to the minus 19. Even harder to take off the third one. So what we do see here is that the majority of the H plus that came off happened in which step? The very first step, because it's much easier to do. Forget there, maybe, go backwards. There we go. So in a polyprotic situation, if you're asked to just calculate the pH of the solution, it is almost a safe bet in most situations that you could take the H plus from the very first one that comes off, and that's essentially going to be the majority of the H plus that comes off, and you could calculate the pH right off of that first step, which I think was your question earlier. So you can, in most cases, pretty safely assume that not much is going to come off in that second or even that third step if there is a third one, and you could just calculate the pH based off of that first concentration, which was the last thing I think we needed to do here. And if we did that, we get minus the log 1.94 to the minus 1. Gets us a 0.71 pH, which I would say is acidic for sure. Yeah. So polyprotic acids, as is demonstrated in this problem here, basically much harder to continuously take off those H pluses, which is why we typically will see on that table that we saw a decrease in the Ka value as you go from Ka1 to Ka2 or even to Ka3. And again, like I said, if it's just a straight up question of what is the pH, you can safely do the first one and be probably pretty safe. If you have a question like this question, which wants to know what is everybody's concentration all the way down to phosphate, you got to kind of do each step along the way like we did here. But again, if it's just a pH question, you should be okay. Any questions on how to handle polyprotic acids? Obviously, you need to be able to calculate those and figure out all the stuff we just did there. Any questions? That wraps up this chapter, which is 13.